Hi everyone, thanks for having me today. My name is Max. I am a PhD candidate at the University of Pennsylvania, advised by Boon Tolu and Lin Fan. I'll talk about my dissertation work on service boosters, a new concept for data center operating systems. So our setup is a data center. For the purpose of this talk, we can break it down into three layers: services, operating systems, and hardware. My focus is on this middle piece, the operating system. First, I'll attempt to convince you that today's operating systems are not good enough for the data center. I'll then introduce service boosters, a library operating system for the data center, and go through existing pieces of the system I built during my dissertation. So what are the problems with mainstream OSs in the data center? I'll take the example of a web service running on a VM to exemplify how they fail to be tail-tolerant and resource-friendly. First, the traditional separation of privileges between user and kernel space requires data to cross this boundary with every interaction with I/O. During this crossing, all sorts of bad things can happen, such as memory copies and TLB flushes. These increase jitter in service time, driving up tail latency. Second, their native scheduling policies are not tail optimal from a queuing theory perspective. For example, consider the default receive-side scaling policy used to serve network packets to CPUs. It represents a decentralized scheduling technique where some cores can be overloaded while others are idles, which in turn can drive up tail latency. Second, DDOS does a poor job at using data center resources and identifying resource bottlenecks. For instance, if a RPC becomes slow and drives up CPU usage in the VM, the strawman solution is to clone the entire VM, potentially wasting a lot of resources, without even being able to identify why CPU usage increased in the first place. So here's my proposal to move forward: service boosters. It is a library operating system for the data center with the following design principles: fine-grained building blocks, clearly exposing resource bottlenecks; real-time anomaly detection to identify what create these bottlenecks; application-aware scheduling to alleviate these bottlenecks and meet SLOs. So here it is, the architecture of service boosters. You've got three domains: the application domain, the boosters domain, and library operating system modules. Programmers write applications as a pipeline of events using building blocks named service units. Service units can be very fine-grained and exhibit a clearly scoped resource consumption pattern. They're made to be profiled and scaled independently. Some service units can take on resource management roles. This can be directly in line with the application, such as the request scheduling booster I'll present later, while others operate on the side. There is a monitoring subsystem able to identify which unit in the pipeline is under pressure and what is the resource it's asking for. We can also identify performance outliers and take specific actions over them. Applications can run alongside other processes and can interact with the kernel to obtain resources. Here's a bit more on service units. There are three main aspects to them. First, the handlers people program, for example, an HTTP parser. Second, their input queues connecting them to some I/O or some other service units. And finally, the dispatching strategy between each layer of the pipeline. The system takes a declaration of your pipeline and instantiates it on your behalf. Advanced users can customize all three aspects: handler scheduling, event queue management, dispatching policies. Okay, now I want to present three components of the system that I built during my PhD. The first is DDOS, the resource harvesting booster. The second, FINLAM, is a real-time anomaly detection engine. And finally, Persephone, a network scheduling booster aiming to maintain good tail latency for short RPCs. So the DDoS project kickstarted what will become service boosters. The idea was to defend applications against asymmetric denial of service attacks. These attacks target a specific routine in your service stack, for instance, an XML parser, and allow attackers to consume significantly less resources than the defender. The de facto solution to withstand the attack is to replicate the entire VM or container. We built a framework to break down monolithic software into service units, such that we can harvest resources only for the unit under attack. So for example, assuming a service broken down into three stages, If stage 2 is under attack, we can harvest resources for this component only and overall better utilize data center resources. Now, with DDoS, we're not able to identify which request exactly was causing an overload. We could just say that some component was under attack, but not reason more about which request was troublesome and how it was abusing the system. This was very frustrating, and we wanted a solution that could work not only for our system, but also other cloud services. So we built FINLAM, an anomaly detection engine that can spot performance outliers in your service. FINLAM has the following properties. It operates in real time as the request harass the system. It can track requests across the many components of your application. And finally, it's not tied to any specific language implementation, as it uses binary symbols to install probes. Taking an example application running on boosters, FINLAM operates in 3 steps. First, it deploys request mappers at each stage of the request processing pipeline. Request mappers bridge the gap between application semantic and operating system semantics, and map request IDs to thread IDs. Second, we can deploy resource monitors at critical resource allocation functions, for example, malloc, some CPU scheduling functions, or TCP send and receive methods. The resource monitors exploit mapped entries to attribute thread resource consumption to requests. Finally, we train the system to build a fingerprint of legitimate request behavior and share the parameters of this model with the resource monitors. Now, the resource monitors can determine whether a request is suspicious in addition to recording its resource consumption. So when attempting to run more high-performance services such as key-value stores, network function, and inference engines on boosters, we realized that a lot of these workloads were performing poorly because of tail latency problems. And specifically, we found out that one big reason for tail latency was the imbalance between what are very short requests and sometimes very long requests. Either legitimate ones such as these get and scans that you can have in key value store, or also because of performance outliers such as these asymmetric attacks that DDoS and FINLAM were designed for originally. So we looked at existing techniques and noticed that they are not a good fit to handle this dispersion-based blocking. The state of the practice in the data center is receive side scaling, a technique that allows the network card to evenly spread packets over cores. Unfortunately, in queuing theory, this is known as a decentralized first-come, first-served model, which is very tail intolerant. It allows the creation of local hotspots at workers. That is, some workers will be overloaded while others are busy. Recent research have proposed to approximate a centralized first-come, first-served approach through work stealing, alleviating some of the load imbalance. Unfortunately, this is of little help when workloads are heavy-tailed or multimodal. In addition, nothing prevents them to steal a long request before a short one. So another proposal was Shinjuku. They entirely removed RSS and hacked very fast interrupts to implement an approximation of processor sharing, so they could preempt long requests and run short requests. Unfortunately, this solution is very sensible to the underlying architecture. So given that the booster environment already incorporates application knowledge, we figured we could leverage this information to build an application over a scheduling booster and entirely suppress dispersion-based blocking for short requests. These boosters, that we name Persephone, profile the CPU demand of each type of request in the system and reserve score for the shorter requests. So we dubbed this policy DARK, which stands for Dynamic Application Aware Reserved Scores. It's a non-work conserving policy with surprising results. So we created a two-phase booster that first takes requests from the network, classifies them, and store them into typed queues. In the second phase, the booster dispatches requests to their allocated service units, and we simply exclude longer requests from core reserved to shorter ones. Here's an experiment with the booster serving a RocksDB workload. It's a relatively even workload with 50% get and 50% scan requests, but note that the scan requests are more than 400 times slower than the gets. We measure the tail slowdown, that is, the request response time over the average service time. To maintain a slowdown SLO of 20, Dark can sustain 2.3 and 1.3 higher throughput than Shenango and Shinjuku, respectively. The counterintuitive result is that, in contrast with our policy that purposefully idle cores for GET requests, here we put one core idle to protect the short request. The work-conserving policies are wasting more CPUs than Dark to maintain a tight SLO, because they must run at a lower utilization to meet this SLO. Okay, so to recap, I presented Service Boosters, a library operating system that draws aspects of security, systems, and machine learning to improve performance, reliability, and predictability for cloud services. So thank you for your time and attention, and I am happy to take any questions.